Hello everyone. Ayten is a student, mathematics student technology, and she will start her third grade this semester. And we studied point-set topology, especially the Tychonoff Theorem. And despite of being this first real abstract subject in mathematics, she did a wonderful job, and I hope you will enjoy it.
Hi everyone. Today I will talk about Tychonoff Theorem and its application. First, we will define the topology, and we will discuss the concept of bases. Then we will explore the product topology and how it is formed from Cartesian products of topological. Then we will look compactness. And finally, we will look at the Tychonoff Theorem. The Tychonoff Theorem is a fundamental result in topology, asserting that the product of any collection of compact topological spaces remains compact in the product topology. And in this presentation, we will review key concepts in topology, explore product topology and compactness, and discuss the Tychonoff Theorem. So, the definition of topology is a topology on a set X is a collection tau of subset of X that have three properties. First, the empty set and the whole set X must be in tau. Then the union of the elements of any subcollection of tau must be also in tau. And the intersection of the elements of any finite subcollection of tau must be in tau. So when we have a set X that has a topology tau defined on it, then we will call it topological space. Let us look what is a topology. In this example, we have a set X, which is like this, ABC. And there are many possible topologies on X. In figure 1, we can see that this represents a topology, since it includes the finite intersection of X, their unions, and the whole set X, and also the empty set. So, are tau, and it's a topology. But in figure 2, we can see that this not represents a topology, since it does not include the intersection of AB with BC. You can see that. So this tau is not a valid topology. Let's look at the definition of bases. If we have a set X, a basis for a topology on X is a collection B, and this basis element has two conditions. For each X in X, there is at least one basis element B containing X. And if X belongs to the intersection of two basis elements B1 and B2, then there is a basis element B3 containing X inside the B1 intersection with B2. And the product topology says that we have S beta, the collection of sets. S beta is taking pre-images of open sets in X beta, and the union of this collection is denoted as S. The topology generated by the subbasis S is called the product topology. In this topology, the space of products of X alphas for each index alpha, this is called as a product space. So the definition of cover is a collection A of subsets of its space X is said to cover if the union of the elements of A is equal to X, and if it is called an open covering of X if its elements are subset of X, open subset of X. And a space X is said to be compact if every open covering A of X contains a finite subcollection that also covers X. For example, the real line is not compact for the covering of R by open intervals like this. We cannot find a finite subcollection that covers the real line. For the Tychonoff theorem, I want to give a lemma. Let X be a set and let A be a collection of subset of X having the finite intersection property. Then there is a collection D of subsets of X such that D contains A and D has also the finite intersection property. And there is no collection of subsets of X that properly contains D has this property. And Tychonoff theorem says that an arbitrary product of compact spaces is compact in the product topology. Now we will look at some examples. First example says that products of Linderoth space are not necessarily Linderoth. Let X be the real line with the Lorentz topology. This topology has a basis consisting of half-open intervals of the form like this, where A is less than B. It is known that X with the sorting-free topology is a Linderoth space, and Linderoth space is meaning that every open cover has a countable subcover. We consider the product space of Cartesian product X with itself, where both factors X are equipped with the sorting-free topology. It turns out that the product space is not Linderoth. To see why, consider the set F, X to minus X. This set is discrete in our product topology, product space. And since there are uncountably many X in R, we cannot find a countable subcover of F. So the product of Linderoth spaces are not necessarily Linderoth. Next example is, let's U alpha is a subset of R for all alpha. If U alpha is closed and bounded for all alpha, then the product of U alpha is also compact. Since U alpha is bounded, we can say that it's contained with some interval minus m to m for a certain m, which is greater than 0. Suppose that the interval is closed and bounded, but not compact. This would mean that there exists an open cover A for this interval, such that no finite subcover can be found. However, since our interval is closed, it cannot be written as the union of disjoint open set and a closed set, which would contradict its structure and as a closed interval. And this creates a contradiction because a closed interval like this allows for a finite subcover. Therefore, we conclude that our interval must indeed have a finite subcover, meaning it's compact. Thus, we can select a finite number of open sets from this cover that covers minus m to m. Consequently, this finite subcover will also cover U alpha. This shows that U alpha is compact. According to Tychonoff theorem, the product of any collection of compact topological spaces is compact in the product topology. Therefore, product space U alpha for all index alpha, where each U alpha is compact as well. In conclusion, the Tychonoff theorem tells us that if we take the product of compact spaces, the result is still compact. This is an important result in topology. To remember compact spaces, say compacting products, this term is useful in many areas of math.